Hello, in this video we're going to look at the generic quartic polynomial function as seen here, and we're going to consider all the possible graphs that can be formed using this function and answer some questions about those graphs. So one thing that I want to point out is that we know that these coefficients a sub 0, a sub 1, a sub 2, a sub 3, and a sub 4 can be any real number, negative infinity to positive infinity. They can be assigned any value at all, except that a sub 4 cannot equal 0. So in other words, this term right here cannot have a 0 because 0 times x to the fourth power would result in that term becoming 0, and then we would no longer have a quartic polynomial function. Instead, this term would be the highest degree, and then we would have a cubic function. So that's the only restriction on the a parameters. Okay, so the next thing I want to look at is the questions that are being asked. Well, even before we look at the questions that are being asked, one thing that we can do is we can type this into Desmos and kind of play around with it a little bit to see what we can notice. So if I do that, you see here I have the function typed into Desmos, and right when I first do that and set up the sliders, Desmos always makes all the values of the sliders to be equal to 1 to start with. But remember, those a parameters can be any number at all. So I can change the look and feel of this graph just by changing these values. And we can look and see, oh, what's happening? Oh, now look, now I'm getting some other images, some other curves popping up here. I'm getting some different concavities. I'm getting some different relative maximums, relative minimums. Okay, and you can see that as I change that value, the look and feel of the graph kind of changes a little bit. Okay, if I make a sub 4 negative, then my end behavior changes, and instead of both ends going off towards positive infinity, now I have both ends going off towards negative infinity. So oops, I had a 0 in there for a minute, which of course then gave me the cubic function. But you can play around with that and you can kind of get an idea. Now these are just ideas because it's impossible for us to look at all the infinite possibilities that this function can graph. So let's go ahead and now go back to the actual function. Let's look at the questions and see what we can know about these questions. So the first question is, f of x intersects the vertical axis in one and only one point. So is that a true statement or a false statement, and why? So in order to answer this question, we have to understand what it means for the function to intersect the vertical axis. So I'm just going to, over here on the side, draw a little set of axes. This one right here is my vertical axis. And I know that if I have a function and the function crosses that axis here, that is what I call my vertical intercept. I do know that any function can only have one vertical intercept, because if it crossed this vertical, if the function were to cross this vertical axis in more than one place, that would give us an input with more than one output, which of course is not a function. So by definition of a function, I know that there can be only one vertical intercept, so I know that this function can only cross that axis in just one place. But there's a second part of this. It says it intersects the vertical axis in one and only one point. So I know the only one point is true, but is it actually required for there to be a vertical intercept? Is there for sure one spot where it will cross. In other words, how do I know that my function doesn't look something like this and will never cross that vertical axis? And one way to know was we played around in Desmos and we saw that we were always crossing over that vertical axis no matter what we put our a values to. But how can I show that more algebraically? I can look and say, well, what is always true about the vertical intercept? And that is the fact that in a vertical intercept, the input value is zero, and then some output value. So if I were to come back here and evaluate that function at 0, this would give me a sub 4, 0 to the 4th, a sub 3, 0 to the 3rd, a squared, 0 squared, not a squared, sorry, a sub 2, a sub 1 times 0 plus a sub 0. And now when I look at all of these, I see this term becomes 0, this term becomes 0, this term and this term both become 0. And so what I'm left with is f at 0 is actually equal to a sub 0. And so now if you go back into your Desmos application, you can see here, right now a sub 0 is set to negative 4.6, and it does indeed look like my vertical intercept is negative 4.6. I can scroll up I can move my slider up, and you can see that, yes, indeed, I go all the way to 10, my vertical intercept is indeed at the output of 10. So no matter what my A0 is, that is my vertical intercept. And we can see that mathematically here as well. So for question A, that statement is a true statement. And those are the reasons why. There always is that one point, f of 0 is equal to a sub 0. So my vertical intercept will always be 0, comma a sub 0. And I know that there can't be any others. There wouldn't be a function. Okay, so let's look at the next one now. B. B, this statement is f of x intersects the horizontal axis in at most 4 points. And then I'm going to kind of look at B and C at the same time. C says f of x intersects the horizontal axis at least once. So I'm going to go back over here to Desmos, and just this one example that I have here right now in Desmos, just by chance, shows that this function f of x is not crossing the horizontal axis at all. The horizontal axis is, the whole graph is above the horizontal axis. So I can tell just by looking at this graph that statement C, f of x intersects the horizontal axis at least once, is going to be false. And it is false because I can produce a graph that shows that to be false. And so C is going to be false. And because both ends are going in the same direction, both ends, let's say, are going to positive infinity, and the whole graph is shifted up above that horizontal axis, there's never any need for the graph to go down below the horizontal axis. And so you can say it's false because you could have a situation that looks like this. Okay. But what about B? It intersects the axis in at most 4 points. So we already know it doesn't have to intersect it at all, but how do I know that the maximum number of intersection points is 4? And the reason we know that is because by definition, if I have a polynomial function of degree 4, then the most number of zeros that I can have is 4 zeros. So the degree matches the number of zeros. And so this is true. Fourth degree implies 4 maximum zeros. Okay. All right, so now let's go to the next one. And the next one would be D. And D says, for very large input values, f of x behaves like the graph of y equals a sub 4x to the fourth power. So I have y equals a sub 4 x to the fourth power. And the statement is saying that this function right here would look just like this function or behave just like this function. And now this is for large values of x. So let me go back over to Desmos, because one way that we can show this nicely is I can say, well, you know what? Let's just make another function here on Desmos and graph it, and then look at some output values. So here's g of x. We can see here that g of x and f of x are not behaving in the same way when x is like between -2 and 2. There's a lot of changes, a lot of differences between f of x and this g of x. But one thing I can see is that as even like not even super large values, just like right after -2 and +2, I see that the function, both functions, are shooting off towards positive infinity very quickly. And so already I can see that their behavior is the same. But then I want to look and see, well, what about for large values of x? Because that's what the question's actually asking. And so, well, I can type in some large values of x. I could type in, we don't have to go that big at first. What about f at 100 versus g at 100? They're very similar. They're almost identical. I can say f at 1000 and g at 1000. Again, they're so close. They're even closer than they were before at 100. Now, when x is 10,000, you can see that they're both pretty much equal to 2.2 times 10 to the 16th power. That's a very large number, but the point is that both of these graphs are shooting off towards positive infinity as the x values get larger and larger. So they are behaving in the same fashion. Another way that I like to look at this is I like to look at end behavior and notice that um, I like to think of it as like the money in my bank account. So if I had a function, let me change colors here. If I had a function y equals 3x squared plus 7x plus 8, and if I'm thinking about, okay, this represents how much money I have in my bank account, when x equals 1, I would have 3 plus 7 plus $8 in my bank account. When x equaled 10, I would have, okay, what's 10 squared? 100. That's 300 plus 70 plus 8. When x is 1, all the 3, the 7, the 8, they're all equally important. But when x is 10, that 300, it means a lot more to me than the 8. I still do care about the $8, but not quite as much as I did before. What about when x is 100? Well, if I look and see what is 100 squared, I get 10,000. So that would be 30,000 plus 700 plus 8. Now I can see I've got $30,000 in the bank. This 8, I don't even care about anymore. I'm not even going to notice if it's missing. So this term over here, let me get a different color. this term over here starts to become insignificant as x gets larger and larger. So let's continue on. Let's make x even larger. What if x was 1,000? 1,000 squared is 1 million. So that's 3 million. I think I have the right number of zeros in there. Yeah. Plus 7,000, right? We've already decided that the 8's no longer relevant. So now I'm just looking at these two terms. Already I can see that now, as x gets larger, this 7x term also becomes insignificant. And so in reality, the amount of money I have in the bank becomes really just dependent on this first term here. And that's, we looked at that in the presentation when we talked about end behavior of a polynomial function. And we said that for large values of x, the polynomial function behaves like the leading term in the function. And so that is what this question was asking. And so the answer is true, because for large values of x, the polynomial function will behave like that leading term. Okay, and then now E says that f of x always passes through the origin, and that statement is false, because if we look back at A, we could see that the vertical intercept is always 0, a sub 0. So the only time that f of x will pass through the origin would be if a sub 0 is 0. So, so it's definitely false that it will always pass through the origin, because it will only always pass through the point 0, a sub 0. All right, I hope that helps. I saw a lot of great discussion out there, and I just wanted to point out some additional ways to look at these questions and statements.